Hello, everyone. Thank you for joining our today's presentation. My name is Zuzana Fabusheva, and together with my colleagues, Paul Karam, Director of Engineering at Quanser, and John Pineros, Quanser's R&D engineer, we will be your hosts and webinar moderators today.
All right, thank you, Susanna, and thank you everybody for joining us. And it's our pleasure again today to host all of you to talk about some really interesting developments that we've been doing, albeit from home, and then we're all doing our best to get up and running. And you'll see some of our home offices as we continue to develop these exciting applications around, the Quanser self-driving car research studio, specifically around the QCar. So for today's webinar, we are going to go through some technical demos, and then hopefully you find them useful and engaging. And a lot of what we're going to be showing you are things that are still in development and things that we're working on as we continue to release all the software examples and applications all around our self-driving car research studio. So before I have my own set of demos, and then I'll let John, my colleague, go through a fairly extensive demo of localization as well. So I always like to start all of our presentations with this slide, just to remind everybody, ourselves included, but all of you as our guests, what Quanser is all about. So Quanser is an academically focused company. We've been in this business for 30 plus years. All we do, our business is for engineering educators and engineering researchers around the globe to really be able to, ask those challenging questions and work together to come up with the answers to those questions. So really, it says it all in our name. We are focused in academia, we are focused in engineering education and research, and we hope to work with you to strive to whatever makes you successful, be it a class, a research project, a thesis, whatever your goals are. We want to make sure that we can work with you to achieve those goals. And another great approach that we take, and something that I always like to begin with, is to remind everyone that from day one, our approach to all things engineering, specifically in the areas of robotics, control systems, mechatronics, has always been an open architecture approach, meaning we want to keep all our systems open and accessible for students to, at the very first time, be able to bring theory to life and be able to really understand, simple principles like what is a transfer function, how do you take a voltage and how does that transfer into a speed and mechanical system, for example, like you see on the left. And that whole ethos and philosophy has stayed with us for 30 plus years, and you can see it in our most recent research platforms like the Quanser drone on the right, and what we're going to be talking about today is the QCar. So it is a research-centric platform where we do everything we can to make sure that we've instrumented it appropriately. We've optimized all the I/O and the hardware at the lowest level to expose it to the software at the highest level to enable you, the researchers, to be able to do anything you want to do and really push the envelope of what's capable along the lines of self-driving research. So here is the Quanser car, the QCar. Today we are going to be focused predominantly on vision applications, but as you can see from this image, there is more than just cameras. We did go fairly extensive on the cameras. We are going to be talking about our Intel RealSense RGBD camera that's front-facing here. Plus we have 4 cameras around the vehicle that are directly piped into the GPU of the NVIDIA platform that we've chosen for our QCar, that give you full 360-degree view as well. So you have the RGBD camera on top, plus the 4 CSI cameras that give you a 360 view over and above all the other sensors that you see here. So we really go to town on making sure that everything is accessible, everything is instrumented, and really nothing is left wanting for you to really be able to do some engaging applications and really push the envelope for your research. So it's just, what we're going to be showing you today is sort of a mix and match between both the RGBD and the CSI cameras. So the RGBD, it is a fairly recent Intel release. It's the Intel 435 camera that, gives you some very high resolution plus high frame rate images. So you can see right there, it gives you depth and RGBD, so you can be able to segment your image, find the stop sign, and then detect when you're close to it for you, for example, here, basic stop and go application. Over and above that, like I was mentioning earlier, we do have these 4 cameras that are stitched together around the vehicle, and you can put it, you can obviously access them all individually, and you can stitch them together in a, long video or wide video strip like this to be able to see all around 360 degrees around the vehicle. Over and above the low-level hardware that we've instrumented on the car, we have always, made sure that our access to all our instruments, especially our research applications, is open architecture. We predominantly leverage the MATLAB Simulink workflow, but it's not limited to just that. And you can see with our applications here in and around all the components of the self-driving car research studio, we really want to expose more than just the low-level C, C++, or the typical MATLAB Simulink experience that you expect from Quanser, but we want to also expand that to things like ROS, Python, and TensorFlow, and so on. We do believe that there are many artificial intelligence and machine learning algorithms that you can implement and research on this platform, and so we want to make sure we're leveraging sort of the tools that make the most sense for those applications as well. And over and above the car itself, the self-driving car research studio does come with reconfigurable roadways as well, so that once you get familiar and start developing some of these applications, now you can start architecting your lab in different formats, and then introduce more and more vehicles. And when we fully expect many of these vehicles to come in and communicate with one another, communicate with the infrastructure, and being able to do many of those other types of research as well in terms of V2I and V2V communications. So here's a very quick video that shows it's keeping the lanes by the CSI cameras and then using the RGBD camera to also look for any distance or any obstacles in the way to stop it. So that's a very quick video showing you how you can leverage both sets of cameras within the same application. Today we will focus on the MATLAB Simulink workflow in terms of the user interface, but depending on the application you're doing, you might choose to do one other, many of the other software environments that we support as well. So you can see here, this is my basement. It's given the current pandemic. This is I've been fairly fortunate that I had the space down here, so I laid out some of our roadways, and this is a steering application. What I'm trying to do here, and I'll get into the algorithm in a second, is not just keep the yellow in the middle, because it's not doing a great job of doing that, but I'm also augmenting, staying on the yellow line, plus predicting what's coming down. So it's looking at upcoming turns and trying to compensate for that while maintaining a decent speed. And I'll walk through the algorithm that we've implemented there as well. So basically the algorithm that I just showed is fairly straightforward in what it's doing. We're using our image capture blocks within Quark. So Quark is our real-time software that allows you to extend a Simulink diagram to be able to run it on real hardware in real time, and all the while it's running, you're getting all of these image streams that I was showing in the video through these video compressed display blocks. Basically, the car is processing all of this full algorithm on the vehicle itself, and then streaming the printed information to my user environment on my PC as well. So that's what those image blocks do. So just very quickly, what this algorithm was doing is capturing a 640 by 480 image, displaying the original image, and then I'm selecting, so looking for a region of interest, in this case the bottom third of the image, because I'm mostly interested in detecting the lines. I'm then transforming it from RGB to the HSV space. It's a little bit easier to threshold and be able to distinguish different colors and parameters in that space. And then we do a simple color thresholding. It should be an HSV color thresholding, where I'm just particularly looking for the yellow in this case. So that then I get a sort of binary image coming out, and then we've written a couple of algorithms that extract from that binary image where the center of that line is, and plus a we try to look for what the slope of that line is as well. So this, the angle. So we're looking for where's the center of that line plus the angle of that line, and then I'm putting different weighting on one versus the other. As you can see here, I'm trying to go a little bit faster, and so I want to make sure that most of the weight of my control or my steering command comes from the upcoming slope or upcoming turn that the car is seeing. And so, this is a simple example, but what I'm hoping to do moving forward is having these be dynamic, meaning the faster I go, I want to start looking ahead further, and being able to really, keep the car on a certain path while predicting or looking ahead to say where the road is coming ahead to make a decision based on that as well. So more development to come. But the interesting thing, the next video I want to show, I've taken this exact same algorithm and I've applied it directly onto a new project that we've just been working on, and this is our virtual labs, our Quanser interactive labs. This is the virtual QBot, and the QBot is our entry-level mobile robotics, sort of the introductory version of the QCar. And the good news here, what I wanted to show is that exact same algorithm. I just targeted, instead of targeting my physical car that was running around in my basement, I just pointed at our virtual QBot model that's running there, and it's giving me sensor information based on the Unreal Engine that we've implemented this system in, and I'm able to apply the exact same algorithm to provide similar performance on a very different platform. And then finally, I just want to end with this video. And so this is another work in progress that we're doing. So we're leveraging, some more of the sort of mixed space of virtual and real, and being able to, as you can see in the top left, the actual vehicle is driving in an open space, and then we are localizing that. And my colleague John is going to show some methods of localizing where the car is within a space. Once we have that localization information, then we can augment, like in an augmented reality fashion or mixed reality fashion, a cityscape or some environment over and above it. So as far as the car is concerned, it's seeing the real information, plus we are injecting the virtual city or the virtual environment within its sensor stream as well. So again, still a work in progress, but we're very excited about where this type of technology can take us in the future. So with that, I'm just going to pause right there, and I'll hand over to my colleague John, who's going to go into a more in-depth demonstration of image processing, and in this particular example, how you can leverage image processing for localizing the car in a open environment. Over to you, John.
Thank you, Paul. So hello, everyone. I'm John. So today we'll be looking at an advanced image processing application using the QCar. As Paul mentioned, Quanser is a combination of question and answer. So the question we're attempting to find an answer for today is to be able to figure out where we are in space. So localization. There's multiple methods to do so. We'll be going through one today. Just as a brief agenda of what we'll be going for is a little bit of a motivation as to why localization is important, running through an example with the QCar itself, and then I'll leave the floor open to questions at the very end. So motivation, where am I? Just as an everyday example, today I'm here at the office, given the situation that we are in today, I would have gone out for lunch afterwards and then gotten something. But we as people, we're perfect, so we can figure out where everything else is in space. We can build a virtual map and eventually get to our final location. Sometimes on our mobile vehicles, that's not necessarily the case, and we have to get a little bit more tricky. Now, one example of just figuring out where we've gone to in space is using dead reckoning. But if you're familiar with some of the implementations, dead reckoning is prone to drifting. And so if I was simply just to close my eyes and get from point A to point B, I probably won't make it to my final location. So we have to figure out something a little bit more interesting. So looking at that, how would I actually make it from point A to point B? So what would I need first? So ideally, I would have a map. And so maps are nice because if I have a very detailed map, I pretty much know where I need to go. But that's not always the case. So if I don't have a detailed map, maybe I would want to build one of my own. But that map's reliability and usability depends on how accurate my estimate of where I am in space, which is hopefully what I tend to give an example for today. We're looking at localization. as one of the building blocks for a potential SLAM algorithm at some point. And so what we'll be looking at is, given some key information in space, let's try to figure out where we've gone, specifically focusing on image processing. So what are some different methods of localization? So if you're familiar with our AVRS system, it has a motion capture system, which is nice because it gives us the location of our drone in space. And if you have multiple agents, it gives us the location of where they all are in space. Externally with a car, you can have a GPS. It tells you where you can go. But both of these methods I consider cheating in a sense that they've already answered that question for you. But more specific, they rely on you having an available connection, either to a motion capture system or to a GPS system. So if you're GPS denied, that kind of is no longer available for you. The QCar also has a LiDAR, so we can use that as a 2D LiDAR to figure out where objects are in space relative to the car. But we also need to process that information to figure out what are some of our landmarks. In the example I posed earlier, I wanted to go from where I am to one of the locations nearby, but I need to figure out when I need to make left and right-hand turns. So having more information than just where objects are in space is going to be key. And so because images are nice and they give us a little bit more information, we're going to be looking at using the cameras and a vehicle model to estimate where we are going in space. And so on the QCar, as Paul mentioned, we do have a sensor suite. The RP LiDAR is on top to measure depth. We'll be focusing on the Intel RealSense. And I could have used the CSI cameras, but just for the sake of simplicity, I don't want to worry about image distortion. So the Intel RealSense gives me a pretty much distortion-free image, and then we'll worry about distortion if we were to use the CSI cameras later on. Now, part of this algorithm also depends on something called AprilTags. So just in case you're not familiar what AprilTags are, they were developed by the University of Michigan, and basically they're fairly useful in robotics applications because they were designed to be a 2D fiducial, and so they can encode a lot of information. Not only that, they belong to a specific set of families. So if you see in the example here, a very common tag that you can find available is the family 36H11. And then within that family, there's a specific subset of tags that we'll be using. For example, on our demonstration today, we'll be using IDs 0 and 2, but you can use as many as you'd like. And their AprilTags are useful because they are they can give you good accuracy in terms of detecting where the AprilTags are in space, and they're also good at being detected at far distances, which for our localization algorithm is very important. Now that we've given a little bit of motivation about localization, what we'll be using in space, now let's actually do the physical setup. And so here we are at my house, second floor, but let's pose a problem. So we need to figure out an origin of where we are in space, defined by the green coordinate axis using a right-hand configuration. And what we'll be given is the position of the QCar at the end of the example with respect to that inertial frame. Now, the only thing I know in this example is the location of my AprilTags and where they are in space. And then via some clever image processing and some frame conversion, I'll be able to figure out where the location of that body is in space. And so what does that information flow workflow look like? So we're going from left to right, where first we're going to be analyzing what is my AprilTag information and why that's useful. Then passing that over onto the car using its intrinsics to get some extrinsic information of where we are in space, do some clever reference frame conversions so that we can actually figure out our body pose in our inertial frame. And then finally, some sensor fusion, where we'll be giving the position of the car in space and then comparing our ideal vehicle model and what it's telling us where we are in space versus what our AprilTag localization algorithm is and what where we are in space. And so if we look at our first section, our AprilTag, and what is it actually doing? So the first chain in our workflow is actually analyzing the image and figuring out what AprilTags have we actually found. Now, the image find tags algorithm basically compares any AprilTag in our image to an ideal AprilTag, and it gives us a homography matrix as well as the location of the center and the corners of all our tags. Homography matrices are important because it lets us know how the AprilTag in our image is oriented with respect to an ideal tag, whether it's skewed whether it's rotated, which is very important because in our case, it lets us know how our camera is oriented with respect to the car. But we need to do some more processing because for now, all we're interested in this example is looking at our captured image into the and how that compares to that ideal AprilTag. And so once we've figured out what our AprilTag information is, we go on to the meat of the example and the trickier part, which is actually the camera-based post estimation. And so we have various groups in here going from left to right. We can look at group 1. And so what do we have here? We have the camera information with respect to the board. Now, if you're familiar, what this is actually doing is giving us the camera model. So if you're familiar with the camera model, here's what it looks like. It depends on a couple of matrices. Going from left to right, the first matrix lets us know our pixel dimensions and then measuring that onto real world coordinates. And so what this allows us to do is give us information of our sensor to let us know this many pixels in the left or in the U and V coordinates. What does that actually mean in our image? Our second matrix actually gives us our focal point so that we know how far we are from our image. And then our last matrix is actually a transformation matrix. And this is where the homography matrix from the AprilTags comes into play. Because our homography matrix lets us know how our camera is oriented because of how skewed our AprilTag is in our image. But this entire section is just telling us this is our camera, how far away it is from the board, but it actually doesn't tell us where we're located in space. We need to do some more frame of reference transformations in order for this to make sense. Now, at the beginning of the example, I mentioned that we had measured the AprilTag location in the inertial frame. So this is going to be very important because this will serve as a transformation that allows us to go from our camera to our inertial frame, which is what's being done in group number 1 here, where we're actually taking in our camera, transforming it to the board, and then taking that and transforming it into the inertial frame. But this still isn't the complete picture because what I'm interested in is the body pose of the car in the inertial frame, which is where group 2 comes into play. In this case, we're transforming the location of the camera into the body frame so that we can figure out 2 things. Eventually, what our final rotation matrix looks like to go from my body to my inertial frame, as well as how rotated I am in space, which is the second output. And that rotation matrix is going to let me know my heading in space, which is my third input, my third component of my pose estimation. Now, I mentioned earlier that we are going to be doing some vector calculations. And so basically what we're interested in is the output that we have for our vector, which is going to, of our position vector, which is going to be the summation of 2 components. It's the summation of where my board is in space, which is input here, and then given our camera model, where our camera is located relative to the board in the inertial frame. So if we started at the origin, we're going to have a vector that points directly from the origin to the board and then back from the board to the origin, letting us know that we're located at 0, 0, given some arbitrary heading angle. And so as you can see here, it's a rather complete example, but it's dependent on a couple of things that we'll be analyzing later on in the video presentation. But this is just a subcomponent of the overall model that's running within the QCar. As we look at in here, this is the actual complete model. What we've touched upon is just this post estimation with AprilTags. We are also running in the same model a theoretical and simplified bicycle model of the car that takes in encoder and gyro information and can also give us a pose rate of how far we're going. And then we can fuse that with our camera information to get a fairly accurate estimate of where the car is in space. We'll be looking at how that estimate looks like afterwards. But we will also be comparing what our vehicle model tells us versus what our camera model is telling us that we are in space. And so as you can see here, all our subsystems are also color coded depending on what functionality is happening in the background. So we see anything that's essential in the sense that it's either reading or sending an output is colored in red. Any type of data interpretation is being done in green. So being able to transform our camera information as shown in the pose estimation with AprilTags, or transforming our gyro and encoder values into a vehicle model is being done in this subsystem. I'm going to be driving the car around with my keyboard. I won't be showing it, but just to let you know where that information is being set up is in the user interface, which is the purple block that we have here. And again, some interpretation of what those keyboard inputs are meant to be giving a command to the car. Another thing I'd like to point out is this is a multi-rate system. So I am capturing information from my cameras at 640 by 480 at 60 Hertz, but my actual image processing algorithm is done at 30 Hertz. So just to give you an idea that what we're doing in here is not locked into a single sample time. This is the kind of flexibility that we offer in all of our systems. Our Q-drone has something fairly similar where its I/O is running at 1 kilohertz, but we're reading sensor information at a much faster rate. This to give you the idea of how flexible our systems can be and the power of Quark being displayed through Simulink. So now that we have everything set up, let's actually look at what the example is doing in space. So as I mentioned earlier, this is my house. This is the example. We'll be looking at one interesting plot, which is the top right one. So the top right plot will have two values. It'll have a yellow value, which is going to be my estimate for my vehicle model, and it'll have my orange value, which will be my estimate of my pose from my AprilTag model. So as I run the video, I want you to look at a couple of things that'll happen as the car moves around. The bottom right scope is going to be the fused information from my vehicle model, its rate estimate, and the position from my AprilTag model. And so you'll see a trail of where the car thinks it's in space. Eventually, I could augment this with a mapping algorithm so that I can see where my car has gone as I'm moving in space. And so running this example, we'll see everything gets set up, and eventually the QCar starts moving. On the bottom left image, sorry, you can see that we've actually captured the AprilTags, but you'll notice that as the car is moving, if there is a little bit of motion blur, it becomes a little bit tougher to track the AprilTags. And so what ends up happening is my estimate kind of stops for a second, and you can see in the top right image, that actual estimate flatlines for a split second. But because I have my vehicle model, I have another sensor or another method of still figuring out what my position is in space. Ideally, you never want to have just one source of information. You want to have multiple, and that's why we're using sensor fusion in order at the very end to get our final location of the car. And so what a nice summary of our example and what it does is we have a method of estimating the pose of the car on board with our sensors that are on board. In this specific example, I've used the Intel RealSense. I could have used the CSI cameras, or I could have also used the RP LiDAR. I could have combined all of them along with a vehicle model to get a fairly accurate estimate of where I am in space. And just because I lose an AprilTag doesn't mean I'm out of luck. As long as the AprilTag eventually comes back into view, I can then update my estimate of where I am in space, which we can see is a fairly robust example. Now, what are some limitations of using AprilTags as a localization method? They have to be rigid in space. If they end up moving, then there's a transformation matrix that is no longer valid, which is my estimate of where my board is in space. So I have to be careful that that doesn't move. But that is analogous to everyday life. We're using AprilTags as a key component or as a stationary landmark that we can reference our position to in space. So if, for example, one day you're walking outside and a big building disappears that you were used to seeing for a really long time, it can be a little disorienting because now you've lost your frame of reference, or you've lost the key landmark that you usually identify with, hey, that distance is roughly 30 kilometers or so forth. Another thing to keep in mind is the computation that comes with, or the penalty in computation that comes with images at either high resolutions or high frame rates. So that's just something to keep in mind. And for this example, we're limiting the capture of our image acquisition to 640 by 480 at 60 frames per second. So some of the motion blur that we were seeing could be offset if we were using the CSI camera because it can run at 120 Hertz. And so when the car starts making really big movements either left or right, I can still keep my AprilTag in view because I can run at a much higher rate. And so with that, we kind of conclude our example of our AprilTag estimation. And now I'll leave the floor open to questions in case you have any.
Thank you, John. Great presentation. I hope you all enjoyed this. Really what we want to get across are there's just, because of the way we've architected our solution, both the software and hardware, really the possibilities are endless. It's really, whatever your imagination is or whatever your goals are in your research can be implemented by any of the software environments that we are supporting around self-driving car research studio, be it MATLAB Simulink, be it ROS, be it Python, or a mixed bag of all of the above as well. That's also something that we're very proud of as well. So we did have some questions, so I'll take the first one, and then I'll pass them on to John as well.
Okay.
First question is, hello, I'm using a Quanser QBot. How can I use the virtual QBot? That was, I guess, a reference to one of the virtual QBot videos that I showed earlier on. So just go on to Quanser.com. One of the first images you'll see there will be the Quanser Interactive Lab. So Quanser Interactive Labs is our new solution that we just released, predominantly or accelerated by the pandemic itself, the crisis that we are all in. Basically, a lot of our customers, many of our customers came to us and were hoping that we would help them find a solution to take their physical labs that they've been working with for many years with Quanser and put them online. And so in an effort to facilitate that, what we've just recently released, actually today is the first official release of the platform, is the Quanser Interactive Labs. And what Quanser Interactive Labs allows you to do is to take our great physical products and access them virtually and have this be something that you can develop on and give to your students. And our goal is always with our virtual labs, like all our physical labs, is to make them be very repeatable, robust, and have the model be quite specific. And so when you interact with a virtual Quanser product, like a virtual QBot, for example, all of the dynamics, all of its limitations, even down to the frame rates and capture information that you get from it, are accurate to the physical system. And so just go on to Quanser.com, click on that first link. There's a trial capabilities as well for all of our Quanser Interactive Labs. Please take a look there, and somebody from the team will be more than happy to help you. So yeah, so great question. Another question for you, John, in terms of the localization accuracy. What kind of localization accuracy are you able to achieve using this AprilTag method?
So when I was running this example, I was able to get like centimeter accuracy, but that also depends on the resolution of the image that I was capturing. So if you do go through a much higher resolution, accuracy does improve. But as I mentioned, there's a penalty on computation time. So then it becomes a trade-off. So that's why I mentioned that it's nice if you augment this with a different sensor. So if I did want to get something more accurate, or I wanted to use another sensor, just as a fusion example, I would use the LiDAR and then look at the field of view and only interested in points that are within the field of view of the Intel RealSense or of a CSI camera. And then that way I can use that depth information, validate it with my camera, and then move on from there to get a far more accurate estimate.
All right. Another question here that I'll take. This is one of the viewers saying this was great, but I'd love to see some ROS or Python examples. And so, stay tuned. We will be having more ROS and Python webinars around the self-driving car research studio. And definitely a lot of what will be released when you receive the self-driving car research studio will be examples in all of the languages that we support. So this particular webinar, we focus on the MATLAB Simulink environment, and that's the one, frankly, that we are the most comfortable with in general. But with our self-driving car research studio, we are also developing in and have many examples in predominantly Python and also ROS as well. So that's a great question. Another question for you, John.
Yes.
If we don't have any AprilTag captured in the image, how do you localize, or how can you compute localization without AprilTags?
So if I was not to use AprilTags, I could still use the concept of a homography matrix in order to figure out some localization information. The benefit of using the AprilTags is because I know they're robust, and I know if I have a specific sheet size, how big the corner to corner distance is. So if I was to do something without AprilTags, for example, I would want to have landmarks in space that don't move with like a very bright color, and use a feature detector in order to figure out when the car is moving, a feature that's constant in space. And so I figure out what that image is, a position in real in an inertial frame, and then convert it to the image coordinates that are being captured by the camera. I can sort of figure out some orientation information via a homography matrix. And then with the camera model, eventually work my way backwards. The only downside or the only trickiness I see there is you're losing the robustness that come with an AprilTag. So it is doable, but then you run the risk of not being able to get accurate information.
All right. So I'll take another question. There's a bunch of other questions. Does the QCar come with or support radar? So that's an interesting question, and radar did come up. It is fairly niche and fairly involved to support radar. Having said that, we make, especially our research platforms, everything that we develop with at Quanser, we want to make it as modular and open as possible. So we have many different general purpose IO that we developed on the QCar itself. They include different protocols like serial, I2C, SPI, and so on. And so if you have a particular sensor you'd like to put there, just send us a note and make contact with Quanser, and we'll be more than happy to help you find the right approach of integrating it into the QCar. But definitely we fully expect users to put on their own sensor suite and their own payloads on top of the QCar to be able to extend it even more so than what we provided out of the box. There is another question, how much does a university or applied science pay for one car? And so for that, we do have many Quanser representatives, both direct or through our partner companies that work with us around the world. So please reach out to Quanser and we'll put you in contact with the right people. We do just sell to academia, so this is definitely targeted through to all applied science departments and engineering departments. And we'll make sure we can get you the right solution at the right price for your research needs. So please reach out to us there as well. There was one other question about the virtual side of things. So, the demo that I showed as we sort of start really embarking on the virtual environments, we want to make sure that they are supporting the actual physical labs, meaning we want to everything we do, regardless of it, be it our new virtual labs that we've released, or even everything we support around our research studios, needs to be hardware centric, meaning even if it is completely virtual, we fully intend the workflow to be exactly the same, so that once you are comfortable with that workflow, you can deploy it immediately exactly as is, even to the device driver level or to the low level interface, to all our hardware to be the exact same, so that you can go from the virtual world to the physical world. John, another question for you. Does the Autonomous Vehicle Research Studio have support for V2V and V2I? Do you have, what communication standards have you guys implemented?
So the autonomous, so vehicle to vehicle.
Yes, exactly. So about, do we support V2V and V2I? That's right.
Right. So in terms of communication for vehicle to vehicle, it's all within a Wi-Fi infrastructure. So we, as part of our examples, we support a stream server and a stream client. So you could set up that sort of network infrastructure. Looks like a star, where the nodes are connected as long as they're within the same Wi-Fi network, as I mentioned. So that is an example that you can support. In this case, for example, you'd be looking at where one card thinks it's in space versus where another card thinks it's space, and have some clever communication back and forth between them. Now, to environment, a vehicle to environment in scenario, what I would imagine, you would have to have some sort of a smart structure, if you will, that is also connected to the same network that the cars are. So if I consider like a smart turn signal or intersection, where I can kind of control the flow of traffic. If that intersection is controlled by one of our devices and is also within the same network as the cars, then I can have some sort of interesting behavior going forward. But the protocols for communication, at least for AVRS, for example, are TCP/IP. So it's all standard. It's not a custom protocol that we use. So if it's, as long as your specific application supports that, you'll be pretty much good to go. In terms of vehicle to vehicle or vehicle to environment example.
And yeah, just to elaborate on what John was saying. So, whenever we develop any of our systems, our whole infrastructure and approach is to, again, to make it as open as possible. And so we've implemented many different communication protocols and enable them and provide support for them. In the case for the self-driving car research studio, like John mentioned, it is very Wi-Fi based, but because it's open, you can have vehicles communicating with one another. You can have all of them sending their own particular sensor suite of information to the central server, and have the central server be sort of the arbitrator of that information and pass the data along, or even fuse it internally for more information. So really, I keep saying, but it is the truth. Your imagination really is what it's limitless capabilities, because it is open. So it really depends on what exactly you're trying to research and then hoping to accomplish with the different applications there as well. All right, let me see if there's another. So another question about for another customer who has the QBot as well. So they do have the Quanser QBot, and they're wondering if we use it in the same way to communicate to Simulink in external mode. So just to elaborate, what we're showing you here in all of our demos, we leverage the MathWorks and especially Simulink's external mode capabilities. And what that really means is, whenever you develop your algorithm or your controller in Simulink, behind the scenes, when you deploy that controller to the car, what happens is Quark, along with the MathWorks toolchain, compiles that Simulink code into optimized C++ and real-time code, and real-time executable. It deploys that executable on the car, so the car is actually the one that's running that algorithm, and then Simulink at that point, via their external mode interface, becomes your user interface to the system. So it's not really running Simulink in the loop, it's just using Simulink to give you indications of what's happening. So if you remember one of my demos, I had many of those image plots in there. That's just Simulink being used to display things back to me, whereas the actual code is being run in an optimal fashion in real time on the vehicle itself at some fairly high rates as well. So that's again a big part of using our capabilities with all the things we've done within the MATLAB Simulink interface, plus our open software interfaces as well. All right, we have another question here. So from a customer or for research group, we're using the QDrone, and I'm wondering if QDrone can support Python in addition to using the predefined Simulink module. So that's a really good question. And right now, we don't have full Python support for the QDrone. It is a fairly unstable system, as you can imagine. If things don't go quite right, it can fall out of the sky, which is never really a good thing, no matter how robust we've made it, and we have tried our best to make it as robust as possible. But we are looking at different ways to also incorporate Python. That is something we want to really fully explore with our self-driving car research studio. The car is a more stable platform. It's not going to fall out of the sky, and we know that a lot of the AI type algorithms and machine learning algorithms will be Python specific, and so we want to really explore that capabilities on the car, and then hopefully with future revisions or updates to our support of all Quanser products, in particular the QDrone, we want to look at that, but currently nothing currently available. But again, reach out to us and we'll have a discussion about how we can support you in achieving your goals as well. All right, we have a technical question here. This question is about code generation. When I'm trying to use some image processing functions of MATLAB and Simulink with QDrone, the code generation procedure fails. So with the QCar, can I use some of these functions? So, because we are MATLAB Simulink specific, our goal with everything we develop is that you can use any of the Simulink products through the MathWorks environment that support code generation. So if there is something that should support code generation and does not work, then please let us know. That is, we'll get to the bottom of it. It might just be a simple use case that we need to adjust for, or there might be something just not fully fleshed out in that workflow. But definitely any block that supports code generation will be capable of being generated through this workflow. So if you are using other toolboxes, please let us know if there's one particular block that's misbehaving or not functioning as expected, and we'll be able to get to the bottom of it for sure. And with that, I believe that's the end of, I think, hope we captured all the questions. Fantastic questions, everyone. And, we hope you keep the questions coming, and hopefully this is just a start of some of your exposure to what we're developing in and around all our platforms, be it all our research platforms like the Self-Driving Car Research Studio, plus I can see some excitement or some interest in our virtual line or interactive line of products that we've just released as well. So please be in contact with us, and we'll be more than happy to have that discussion with you, to talk about your goals, your needs, and how we can work with you to achieve your success. Thank you very much for attending, and I'll pass on over to my colleague, Susanna.
Thank you, Paul. Thank you, John, for a great presentation. Thanks to all our attendees for joining us today. And we are looking forward to seeing you at one of our future webinars.
Bye, everyone. Thank you.
Bye, everyone. Thank you.